So in this exercise, let us see a few more problems on direct and bending stress. Say we have a rectangular column 200 mm wide and 150 mm thick is carrying a vertical load 120 kN at an eccentricity of 50 mm in a plane bisecting the thickness. Determine the maximum and minimum stress intensities. So first draw the rectangle 200 mm width, 150 mm thick. So 200 mm width and 150 mm thick or deep. Then the load is 120 kilonewton applied at an eccentricity of 50 mm in a plane bisecting the thickness. So this is the plane bisecting the thickness. So load should be placed along this axis. That is, the load is eccentric with respect to y-y axis, or the column bends about y-y axis in this case. So we know that the maximum stress is given by direct stress plus bending stress. Direct stress is load by area, bending stress is m by I into y. Load, and similarly minimum stress will be P by A, direct stress minus bending stress, P by A minus m by I into y. Now we will find each of the terms. So P equal to the load is 120 kilonewton, therefore 120 into 10 power 3 Newton. Then area, width into depth 200 into 150. Then bending moment M is equal to P into E. So load is given 120 into 10 power 3 into eccentricity is 50. Therefore, this will be 6 into 10 power 6 Newton hyphen millimeter. It is not Newton per millimeter. This should be force multiplied by distance. Therefore, Newton hyphen millimeter. Then I equal to moment of inertia. So bending takes place about y-y axis. Therefore, Iyy need to be taken. Iyy equal to dv cube by 12. D is 150 and B is 200. So 150 and 200 cube by 12. Therefore, this is Iyy. Y is the extreme fiber distance from the axis about which bending takes place. So the section bends about y-y axis. So from y-y axis to the extreme fiber, it will be equal to breadth divided by 2, b by 2. Therefore, 200 by 2, it will be 100 mm. Therefore, sigma max will be equal to P by A plus M by A into Y. So we know we have P 120 into 3 divided by area. Then M is we have, and similarly I we have into y. Therefore, this will be 10 Newton per mm square plus, and minimum stress will be direct stress minus bending stress. It will be minus 2 Newton per millimeter square. So we need to plot the stress diagram. So here a load is applied here. Therefore, this region will be compressed and this region will be under minimum stress, or it will be subjected to tensile stress. In this case, we have 10 positive. Therefore, mark 10 positive compressive stress here, and this is minus 2. Therefore, this should be marked in the other way. So tensile, so marked in the opposite direction, connect these two. So this is the stress distribution diagram. So this region will be compressed and this region will be under tension. So the force or stress here is 10 Newton per millimeter square and stress here is 2 Newton per millimeter square tensile. Another example, in a tension specimen, 13 mm diameter, the 13 mm diameter means it's a rod. So it's a tension specimen. Normally we used to find the Young's modulus, or we will be using to find the yield strength of the steel which we use for construction. So tension test will be normally performed in a universal testing machine by applying two equal and opposite forces like this, or pull like this. So this cross section is a circle of diameter d, which is equal to 13 mm. So we know that maximum stress, sigma max equal to direct stress plus bending stress. Direct stress is load by area, bending stress is bending moment by I into y. So P equal to load not given, area pi d squared by 4, pi into 13 squared by 4. Then moment M equal to load into eccentricity P into E. I, moment of inertia of a circle or circular section is pi d power 4 by 64. We know the diameter, therefore we can calculate the value of I. It will be in millimeter power 4. Then extreme fiber distance. So from this axis to the extreme fiber, it will be diameter by 2, d by 2. Therefore, this will be 6.5 mm. Therefore, maximum stress will be P by 132.7 plus P by 140.98, which we obtained earlier, into 6.5. And it is given that, say the condition is given, determine the distance of line of pull. That is, we need to find the eccentricity when the maximum stress is 15% greater than the mean stress. Mean stress means it is load divided by area. It will be also equal to the direct stress. So mean stress load by area. So that multiplied by 1.15, because it is 15% greater. So 1.15 times P by 132.7 will be the maximum stress. We have already found maximum stress using this relationship. So equating these two, P by 132.7 plus P by 140.98 to 6.5 equal to this 1.15 into P by 132. Therefore, P will get cancelled and we can find the value of eccentricity which is 0.243 mm. Thank you for your kind support in subscribing our channel. Keep watching our channel.